This is lecture number 1, and this whole course is about designing phase lock loops. And before we go to the phase lock loop, we'll just see why do we need such kind of things at all. And I can very well say that you use it every time. If you're using any electronics, you use it every time. And forget the electronics means anything periodic which you see in the nature that has some kind of lock in the system. Now we are talking in terms of electronics, that's why is it very particularly we call it as a phase lock loop. So before we go to the phase lock loops, you see the beginning of the PLL lies in something as a realization of periodicity. Means you can read all like periodicity in mathematics or anything, but it is the very like in electronics is a method to realize any kind of periodicity you want, and by having something periodic in nature, you also have synchronous systems, which are like clock systems. So, can you tell me what is like the very basic periodic thing which you observed in nature, which you observe not in nature in your real life before even you come across this electronics like computers or cell phones or anything which basically just is very like it ticks every second, or it means it counts every absolute time. It is something which is periodic in nature. Means look around it, right? Day and night, they are periodic in nature. It always occurs 24 hours periodically. A year which always occurs 365 days, right? And then you will tell me that you always have a 365 days. This is PLL. So you have 365 days a year, but once in 4 years you have 366 days. And you may say this may not be a periodic in nature, but I would come and say this is means there is another kind of PLL which implements actually this. So you count 365, 365, 365, and once in a while 366. Not once in a while, deterministic, right? So if you take an average of 4 years, this is 365 days plus 6 hours. So that is a case of actually a fractional and PLL. You do not realize in an integer number, you realize in a fractional number. Okay, and means all these, whether this day and night or the revolution of the earth or anything is happening as per the forces which exist in the universe, that is at a very, very big different scale. Now think of something which is a clock at your home, which works on like all these electronic clocks works on something as a, so it's not something, but they were all the electronic clocks works with quartz crystal. Okay, and this quartz crystal makes exactly 32,768 vibrations per second, one of the crystals in quartz, right? And that means that is an absolute thing, and it loses like roughly 1 second in 30 years. Loses, or basically it amounts to that amount of error in absolute time reference. And that timing is means how do you means this is not like something you do not need to provide any energy. Every quartz crystal which you are using in your electronic watch that has a current usage, so there is energy consumption happening there. Now if I say, let's say you stop giving the current to the quartz crystal, what will happen? Whether your clock will still run, you lose the time. Or if the battery doesn't give the sufficient amount of current, you may basically die down the oscillations, or you basically die down the, it means you lose on time, absolute time. And if you lose on time, I would say you will be couple of minutes late to the class or to any place, any appointment, right? And think about it, it's like all the electronic watches which are working, they are working with this single crystal. Different kinds of crystal, means this is one periodic thing in the nature. Now if you lose couple of minutes and you do not come to the class, then it is like you are not locked to the class timings. There is some variation in when I start the class, but there is, if you watch Loses Time, there is some variation in your, and you do not come on same time every day. So in some sense, all of you guys are locked to the class which you are crediting. The difference between the crediting and auditing is that the auditing will bring something extra components in your schedule, and then you may lose the log, right? So you need some kind of feedback loop. That is like, if you do not credit it, you will not get a good grade, which you may want. That's a feedback loop which is working, right? You have to do the assignments. So, well, this is all on the side that an electronic watch, which basically gives you a very much accurate amount of time, and within some error of few minutes, you are out of time. Now, think of some of the examples that where it's not about only couple of minutes, where even the seconds matter, even less than like a fraction of seconds matter. So let's say you are talking to your friend on phone and there is a lag, means there is it's not the lag of the conversation that you are speaking and the other guy will speak, so there is obviously a time lag, but you speak and the other guy is just basically holding on the phone and is not able to listen to you. There's an absolute silence, and this silence is not caused by you, but the silence is caused by the delay or the timing errors. There, I think if 30 seconds your phone, you do not hear anyone on the phone, you say, man, hang up, call drop, and you just criticize the operator. So it's like, this is it's like a call on phone where actually you have very, very accurate timings. And for example, you can say, means the clock, you are like, if you have heard of the GSM phones, right? Everyone has heard of it. So there you have all the channel which your phone is tuned to, and the channel which the neighbor's phone tuned to, maybe only few hundred kilohertz away. And if you actually lose your phone clock to another person's, you will not be able to hear anything, because you do not have the right permission to operate on that channel, right? Then if you look at the other case of the clocking, when you are using a laptop and you switch on, like you push a button and you take some time for the folder to open or for the browsing. Moment it comes, man, internet is slow. This is like they say 2 or 5 Mbps, but I don't think I am getting even kbps. Means there you realize Mbps, kbps, and I don't think what will happen if you have gbps. So what gives you that gbps, mbps, kbps is a very, very well defined clock, and you want that to happen at the instant you press the key. So many things happen at the background. The instant you press the key, it takes the instruction, it processes it, and then it asks for the data to come in. So there you can say, it's like, let me just say, I just call it as the internet, which is what speed it is operating, means there also a very fixed clock is working. So this is more of a, it's like more on the electrical side, because I can relate to it. Now look at some of the video side where you are like watching a movie and it is normal speed is 30 frames per second. Now, if you are 30 frames per second is not good for you if you are playing Quake, let me say. Right? It means you need a very fast streaming of the video. You need much more resolution. So you need everything to come at a higher speed. Who maintains that? Means you cannot maintain with your electronic watch for sure, which is where the frequencies are not crystal oscillator, where the frequencies are not more than 100 megahertz. So this is on the electrical side. Now observe this fan which is working, and it has certain rotations per second. And I just say I stop it for a minute and then I start it again. I mean, if something happens to the fan, the motor doesn't get right, it is jerky, right? You can very well observe that. And you can observe that not a 1 minute, you can observe that even for a few seconds, you can say this is not working right. So everywhere, if you see, there are many things which are periodic in nature, which you do not realize, and they are working with some kind of feedback or some kind of forces, like in this case, you will have a certain amount of current going through the motor, which creates a certain force, such that it rotates always at the same speed, given the current is the phase. So all these things, which is like all these things are periodic in nature, and or you can say they need some periodic element in their operation, and if they lose the periodicity, you find it disrupt completely. You find this system doesn't work fine, right? So in all these cases, what happens is that, means other than the fan, which is more of on the mechanical side, I would say you have some kind of source which produces, or which basically gives you a periodic output, and then there is some kind of feedback in the system, which ensures that you always produce a periodic output irrespective of what happens in the surrounding. So in all these, means in order to maintain the periodicity in all these things, you actually have a source. Source is like, you need to have some basic starting point. Now whether you say I will take this day and night occurrence as a source, the rotation of the earth, that can also exist as a source, and you lock everything at a with the day and night, like you do everything fifth day in a week, right? That is again one kind of periodic thing which you are using. But in electrical thing, which we will say is a source, is normally, I will talk about the crystal oscillator. So we'll see what a crystal oscillator is, which is actually a periodic source, plus you have a feedback loop to ensure that you always produce a periodic events insusceptible or susceptible to what extent? To the variations around it. Okay, so just for your information, is like if you leave a human means if you let a human being go in a place where you cannot make out of a day and night, okay, then the human body locks to a time cycle of 26 hours, which is not 24 hours. Means all the activities of the, means it will happen automatically, that the sleeping cycle, eating cycle, and everything, normally it locks to 26 hours. This is more of an experimental side that people have done. So the human also gets locked to some kind of time period. But that's on the story side. Now, this whole source plus the feedback loop, when it produces a periodic event, our study is all about this feedback loop, which I right now call it as a phase lock loop. Now, what is a phase? How to what we are locking? We will see. That is the course about. Okay, so let's begin with the source for periodic events. So any device which can give some output characteristics, any device with output characteristics which are least susceptible with output characteristics which are least susceptible, or I will say least susceptible to PVT variations. That can be used as a source in your system. With output characteristics periodic in nature, means obviously we are looking for a periodic source that we forgot here, and least susceptible to PVT variation. PVT variation is pressure, voltage, temperature, those variations which exist around here, around the electronic system. So the one of the examples is your quartz crystal. Okay. Now this quartz crystal is as such as the chemistry goes behind it. It is a silicon dioxide when arranged in a crystal format. And if it is if this quartz crystal is basically is carved out or is something in a fork kind of you cut out from the crystal, and you can say this can move depending on how you apply the electric field. So this quartz crystal works on the phenomenon of inverse piezoelectricity. It's also called as a piezo piezoelectricity. So what happens is you see these two plates of these two one, right? So you apply the electric field on the two sides of the crystal, and when you apply the electric field, it actually deform the shape. The shape changes, and then you remove the electric field. At that time, it regains the shape, and it creates the electric field in the connecting in the surrounding, and that electric field gets converted into the voltage, and you use that you take that voltage, amplify it, and feed it back. So in this manner, you are actually when you are applying the electric field, you are consuming power. So when it comes in a feedback loop, it produces the oscillation. Means this is like compression and expansion that will happen at a fixed rate. So one of these crystals gives you oscillations. These are oscillations which are like 32,768 oscillations per second. Okay, and it loses on 1 second in 30 years. One of the crystals. And what frequency, like, does it produce only 32,768 oscillations? No, means you can always get some other size, because this characteristic very much depend on the size of this crystal. So you can always cut it out and get different oscillation frequency. So the electrical symbol for this crystal, which is this. So this is not a capacitor, okay? It's not like a capacitor between a dielectric. Don't say that you made a capacitor and you thought this is a crystal. This is a crystal. And a normal capacitor is this, okay? And I think people who are familiar with the transmission gate also you make the transmission gate like this. I think there are many. So the transmission gate is, do everyone know about the transmission gate? Is a PMOS and NMOS. So you have NMOS and this. So don't make an error with the transmission gate and the crystal. They are two different things. Okay. So, and the electrical model for the crystal means you can model all these oscillations using an inductor and a capacitor. And the electrical model for this is C0 LRC1. So, though this is a mechanical device, but you can model the oscillations which are happening in this device with the inductor and capacitor. And if you see the resistance is there, that is basically telling that there are some losses in the system. If you stop giving the current to the crystal oscillator, it will lose the oscillations. Okay. Now, the impedance of this crystal is Z of S is S square plus omega S square. Okay, and your omega S is L1 C1 and omega P is okay. So the actual frequency of oscillation can be adjusted between omega s and omega p by adding some extra capacitance in the extra capacitance around the crystal. So normally you have a certain tuning range that you can change. Means if I go and let's say at the other edges of the crystal I add these two capacitors, some capacitors, right? So surely I am changing the network and I can change the frequency, but the tuning range is very small actually. Okay, so crystal oscillator is one of the really pure source of frequencies in all the systems. Means you may be working at a gigabit per second with a gigahertz of clock, but there will be somewhere a crystal oscillator sitting in the system which will be produced giving you the basic frequency, a pure source in the system. So what are the advantages and disadvantages? Means if I ask you the question that I can generate any quartz crystal which is very pure, then I do not have to study PLL. So the thing is, this crystal oscillator frequency, no matter it's like what they are made of, the crystal oscillator frequency is generally very limited, and that is because of the it's like what dimensions can you carve out and how stable they are. So this is generally lesser than 100 megahertz. Means I would not say this is a very general thing. It's not a strictly thing, because there are oscillators you can find which are other compensated, which can go up to few hundred megahertz also. But not I haven't seen any crystal oscillator which is operating more than a. It means I would suspect anything exists more than a gigahertz crystal oscillator. Normally you get it. I think 400 megahertz crystal oscillator also you can find out. Means they are there in the market. So advantage of crystal oscillator is that it's a very pure source of frequency, and quite stable, or let me just say more or less it is insusceptible to PVT variations. But the big disadvantage is that once you manufacture this crystal oscillator, you have very limited tuning range by using capacitors on the side or changing something in the network. So it has a very limited tuning range, and it is like a one-time thing. Very limited tuning range, and output frequency is limited. Means the absolute output frequency is limited. So let me say, I think if you have heard, you are like nowadays having 2G, 3G, 4G and all, they are all sitting at more than a gigahertz of frequency. It's not possible to use a crystal oscillator and just use that clock. Okay, so absolute frequency is limited for these, and it's a one-time thing. Once you make a crystal, you cannot change the frequency that much. Okay, so that is where everything starts, that I need to operate at a different frequency. But I do not have as pure any other circuit or something which can give me this stable and this pure source of oscillations. So if I ask you this, that we have seen, let me just do this. So electrically we can model a crystal oscillator with some LC thing, right? So if I want to change the frequency, what should I do? Forget the crystal. This is coming from the physical properties of the system. If I want to produce any fixed oscillations and any frequency I want, what should be the starting point? Okay, so what is deciding the frequency of oscillation in this resonator? L and C, right? It's just the inductor and the capacitor. So if I can design an inductor and a capacitor, any kind of value, which I think all of us can do it, and we know that we can design it, fabricate it on silicon, right? So we should be able to get whatever frequency we want. So the starting point is that I have a means I design an inductor, whether you design on silicon or outside, that's a different case. I have an inductor and a capacitor, and what I do, I either charge it with the voltage or a current. So let me just put an ideal thing. So what do? I have a switch here, I have a pulse here. I give the charge to the capacitor, and then I just remove this, disconnect the switch. So this capacitor starts with some charge, means after a point, this means once I close the switch, let's say this is VC, this starts with charge voltage, and then this is an inductor. At time t equals to 0, this was VC and I was 0 at t equals to 0. So can everyone get that if I have this as a network, then the output voltage, let me call this as V out, will be oscillatory in nature, because there is no like dissipative element in this circuit. The capacitor charge will discharge through the inductor, inductor will again charge back the capacitor, and you will always have a sustained oscillations. And the frequency of the oscillation is equals to 1 by under root LC. Means ideally you can do it, right? Any frequency you want, maybe you can get even 10 gigahertz, no problem with that. What's the starting thing is that you do not get any inductor as a real inductor, as an ideal inductor, sorry. All these inductors are real inductors which have a resistance in series, and all the capacitors, they also come with some dissipative element, which is again, let me call this as a conductance, inductance, and resistor. So if I again do the same thing, what will be the output after t equals to 0? Pardon? No, I didn't. Yeah. So you will start, means you may start with, depending on, you may start with some oscillations, and then you will just die down. This is the real scenario. So we are all engineers. So what we do, we go and we actually put an active circuit, and somehow we realize something as a negative resistance, so that the whole network, means this is a simplified thing. So the whole network, if this was the equivalent, let me just call it, this is the equivalent of this LC resonator, then we put a negative resistance somehow, okay. So now again we can sustain the oscillation, right? Effectively, so effectively this circuit is nothing but an ideal LC circuit, if you can realize it that way, right? So I can get the oscillations, and again no need of PLL. And I'm still trying to see why I need PLS. Okay, so what do you think can go wrong with this? At least math. So one thing is you design L as your mathematical equation and you get the frequency, but how confident you are that your mathematical equation and the real inductor will be the same? And then the other thing is, what will happen as the temperature changes? So your all the components which you are means everything has some coefficient temperature dependence, maybe large or small, right? So you have couple of means. First thing is your L, R, and C. They are all susceptible to variations, PVD variations. To some extent or not, that's a different case. Okay. So if your L changes by let's say 4 times, your frequency changes by half the time. Right? It's a 1 by under root LC. Now, whether it's a 4x variation, then I would say it's a really bad design that you do not take into account of the range where you are going to use it. Then the other thing is, you should say as soon as you are having a resistance in the system, you are having thermal noise. So let me just show you what will happen as such. So let's say you realize using this negative thing, let's consider this as, okay, let me just this is sine wave only, which I can't draw properly. So you have if there was no thermal noise in the system, then you had a perfect sine wave. If this circuit is all ideal, means whatever frequency. The question is, this frequency is dependent on your LNC, right? If your LNC are not the correct which you want, then this frequency will be different. So let's say that is okay, we will deal with it. The next thing is, as soon as you are having a resistance in the system, you will have the noise riding over it everywhere. Now, whether the transition happened here or it happened here, that very much depends on the time. No, sorry, depends on the noise. So as that depends on the noise, so your time period actually change. Time period is just the separation. So let me define that thing. Time period is the separation between two zero crossing points with the same slope. So as the noise is there, then your edge of cross means your instant of crossing changes, your time period changes. So you if your time period changes, then it means you are not having the same clock. A clock means an ideal clock should always, in absolute time, it should always count at the same interval. Because of the noise, that you are not counting at the same interval. So your reference period changes, that the frequency changes. So these two things force you to study some kind of feedback loop which compensates all these variations and the problems which we are seeing. And again, I would repeat, if you can have a tunable crystal which can give you as pure as the regular crystal give at any frequency, means PLL can't give you that clean clock. Okay, so if let's set up the problem like, because the problems which we are seeing here due to the variation in the physical component values and the noise. So first one is, so let me say your crystal output is, so crystal always acts as a reference in your system because that is the purest form of the clock which you have. Okay, so crystal output is this. Okay, so even if it appears that they are not periodic in the screen, but assume they are periodic. Okay, so this is the time period of the crystal, and I want to generate a clock which is twice the frequency of the crystal frequency. Okay, this is what I want, desired. So I went and did all these LC parameters. I found the right values and I put it, but what it turns out to be, the LNC component value changes, and what came out was something, let's say, this frequency. This was the real output. Okay. In an ideal clock, every rising edge defines that you covered this much of time in absolute sense. Okay. Now, if the desired case was means if that what I desired that the rising edge of the output clock should happen twice in every reference period. That is what I wanted. But what came out was I am having actually 3 rising edges. Okay. So if I ask you that how can you find that what is the error? What should be the methodology? You have an absolute time reference, which is a reference. You know that whenever, let's say, whenever rising edge on the reference comes, your sound beep, there is a beep sound. Okay, and there's a different, there are a different oscillator. Whenever rising edge comes, there is another beep sound. Simply think it very simply. So, in this time period, in an actual clock, I will hear. I mean, this is the reference period. In an actual clock, I will hear 3 beep sound, right? So if I say for the real output, if let's say T is the T output was the one, if I hear 3 beep sounds in the one reference period, that means my T ref, let's call this as T ref, is equals to this T ref, right? Yeah, T ref is equals to 3 times T output. But this is not what you wanted. So what you wanted was 2 times T output. This is a desired. So what is the error? So let me just put in some kind of numbers. Let's say this is equals to P times T output. And this is what you desired. You're counting in numbers. You're not doing anything much more than that. So if I say what is the error, can you just write in some very, very simple thing? So if I have to say the error is actually equals to, so it's like P, P minus N. This again in terms of like not doing it exact mathematical thing, but it is just like counting based. So if your P is higher, that means you are counting more cycles. If you are counting more cycles, that means the output clock period is lesser. That's why you are counting, that is frequency is more. That means you have to go and reduce the, what shall you reduce if you count more? Okay, let me just put it this way. You have an LC oscillator, you have a freedom to control the capacitor. What you are observing is that I am counting more periods in the reference period. Okay, that means my frequency is more. If my frequency is more, in order to bring back to the same frequency, shall I increase the capacitor or reduce the or decrease the capacitor? Increase the capacitor. So do you think this P minus N is actually a representation of whether your frequency is higher or lower? We everyone agree with that, right? So if I was counting only one cycle, then I say, okay, I need to increase my frequency, I need to reduce my cap. So the thing is, you see that there is a reference which is coming from the oscillator. There is LC oscillator which I have designed. I want the frequency to be twice. I observe something and I say, okay, if this number is greater, I need to increase the cap. If this number is lesser, I need to reduce the cap, right? And I have to do it in a closed loop fashion. Observe and correct it. So the loop, which actually, So the loop which corrects for let me say this is a feedback loop. So this is a terminology which we use very often. A feedback loop correcting for frequency error. So here I am just saying the frequency error, and we are just counting based in this particular case, right? Frequency error is called as frequency lock loop. So I think you would see the term FLL at many places. So how exactly you calculated the frequency error? There are many variations for this frequency lock loop, and that is one part of this course. Okay, all we are doing is nothing but we have a reference source, we generate some source, we try to see whether it is producing exact frequency what we desire or not, and then we go and correct it. Okay, now the second case is, let's say I have the oscillator output, which is so this is the oscillator output, and somehow means after doing this FLL kind of thing, I got the exact frequency I wanted, which is actually twice the, so okay, this period is slightly different. So I wanted twice the frequency. I did the FLL loop and I got a twice the frequency desired output, and I applied the control in FLL and I got the output. Now what happens is, because I told there is a thermal noise in the system, so this edge will actually vary. It may not come at the exact time instant, because as we have seen here, right, that you have a overriding noise on the output. An overriding noise on the output will change the transition edge. So in a mean time, it means in a given amount of time, you will still have the same number of periods. But if you look absolute, it can vary. Like, let's say if this edge moves, let's pick up this. If this edge moves to the right, and this edge moves left, the transition edge, and everything else remains the same. Is all the preceding and the succeeding transitions are the same. You will still count the same number for frequency locking loop. But in absolute terms, you have changed one transition. And it is happening because of the noise in the system. So, means then there exists a loop which actually corrects for the error between, this corrects for the absolute error between the rising edge of the output and the rising edge of the reference. So this delta t means if any variation in the delta t is corrected in a feedback manner, and that is called, so this delta t is an absolute time domain, the error between the output and the input in absolute time domain. This delta t can be so this delta t can also be written in terms of phase, where delta phi is equals to 2 pi times. So okay, let me just say phase is a dimensionless quantity. So I need to define this. Phase is a dimensionless quantity, and it's a measure of how much time you accumulated. Measure of absolute time accumulated, or absolute time passed, you can say accumulated, and normalize to a certain reference. Normalize to a reference. This is very important. To a reference. Okay. So this is how it is defined. So let me just say the time error delta t gets translated to the phase error by this relation, where t is the time period. So you see, if delta t is equals to t, means if I pass t time, then delta phi is equals to 2 pi. So the definition, this is just a definition. Okay, so a loop which actually measures the timing error between the reference edge and the output edge and corrects for the timing error, that loop is called as a phase lock loop. Okay, it's an corrects for absolute timing error between reference and desired output. Now, how we do this thing in a on negative feedback, this thing in a negative feedback manner, that is all the phase lock loop does that. Okay, so this is another part of the course which will be deal with. The last is, so this is quite interesting, and let me just say, initially I told you the concept of leap year, right? You count 365, 365, 365, and then suddenly you count 366. So let me just say, so counting is like 365 days, 365 days, like first year, second, and third and fourth, right? So if I ask you what is, so the total time which you have counted, what is an average time of the year after 4 years? That is 365 days, 6 hours, right? That's an average year is. Okay, now let me just say, if all this, so in the same fashion, right? Let's say I count for the reference clock. We have reference clock. So let's say in first reference cycle, I counted first tref, I counted 2. Second tref, I again counted 2. Third tref is 2. And fourth tref, I counted 3 on the clock. Then what is the average output of the clock? It is, so 4 tref divided by 9, right? This is the average period which I counted. So a loop which enforces this, not an integer. This is not like counting. This is not the case where we always count that within one reference period you should always have 2, 2, 2. No, you can have 2 and then suddenly you have 3. So the average cycle of the output clock period is 4 by 9, right? So the frequency, if I say average frequency is equals to 9 by 4 of fref, which you can say 2 basically 25 of fref. So I generated a frequency which is this is called as a frictional multiplier. It's not multiplying by 2, it's multiplying by 2.25, right? And such kind of PLLs which enforces this relationship are called frictional NPLLs. And this is very much required. For example, I can say your GSM which is operating at 900 megahertz, your each channel is located 200 kilohertz away. So 900 megahertz plus 200 kilohertz, another plus 200 kilohertz. So you require this kind of clock generation in like fractional NPLs to to change the carrier. So this whole course will be about mainly FLL, integer NPLL, fractional NPLL, and in addition we will have DLL, MDLL, means all these things exist. So we will see how the time allows. And yeah, so do you have any questions on this? And we are not doing anything new here. You can see the leap year has already been implemented in that manner. You can just look and means this is a very simple thing. You look how do they come up with these numbers. Okay, so let's stop the lecture here. We'll meet tomorrow.